Aloha and welcome to this module on testing. Now I know in the past I've tended to kind of minimize the importance and relevance of some of the prior modules, but this module is really different. This module on testing could very well be the most important module of the entire semester. And I say this because it's hard to think of another module which can so relieve the stress involved with software development. And as we all know, software development can be very stressful. And it becomes even more stressful as the system gets larger and larger, and it's less and less possible for you to keep the entire system in your head at any given time. And when that happens, you need some kind of help to make sure that what you're doing is not breaking other things that are going on in the system. And that's, in essence, what the long-term developmental property or advantage of having testing is. Testing can benefit in a lot of other ways. It can support contractual compliance and all sorts of things. But the thing that I think is most important is stress reduction. Okay, and so I think you're going to really enjoy learning how to write and execute tests and make them an integral part of your daily life as a software developer. So we're going to start today. We're going to talk about some basic concepts and terminology for software testing, white box, black box, etc. That's going to help you kind of understand the conceptual framework that people have used for testing. And then I'm going to hope that you can start to apply these principles in your testing as applied to the Robocode project, for example. So let's start and ask why testing is important. And there are a lot of case studies in the literature of situations in which the lack of testing has led to disastrous consequences. Here's an error from the National Bank of Chicago where they messed up their ATM transaction software, and 800 customers had their balance inflated by a total of $763 billion. Can you imagine? Almost $1 billion per customer. You wake up one morning and you're a billionaire. It's pretty crazy. Okay, so you don't want to do that if you're a banking software developer. This is I think, perhaps the most famous kind of testing or software engineering disaster of them all. This is a really interesting case and horrific, really. It's called Therac 25. What happened was there's a radiation machine called the Therac, and it was going through various model numbers. And the way radiation machines work is that you have the laser that issues the radiation, or the gun that issues the radiation, and then you have a series of lenses, different lenses that focus the radiation beam in smaller or larger areas depending on the treatment that you need. And so basically the amount of radiation being emitted can be adjusted, and the lens can be adjusted. And if you're radiating over a large area, then you need kind of more radiation being emitted. But if you're radiating over a very small area, you need much less radiation, right? Because it's a smaller area. Well, in earlier models, the way the hardware was designed such that it was impossible to have the lens that focused the radiation into a small area in conjunction with the emitter that emitted large amounts of radiation. You just couldn't get those two to be set at the same time to work, in combination, because that would result in really bad things. Large amounts of radiation being emitted on a small area of the patient. Well, the Therac 25, they went from a model in which there was a hardware control of what emitter and what lens was, in position, to a software-controlled one. They didn't deal with race conditions in the operating system, which was also a custom operating system, which meant that when the operator of the radiation machine started using type ahead to fill out fields, it could result in the emitter, the large radiation emitter, being set in conjunction with the small, the focuser, and people were actually dying from this. So it's really terrible software related problem, and it's a great case study of how software engineering principles, when not applied, can result in really terrible consequences. Another problem: Ariane 5 rocket exploded. This was a buffer or a floating number conversion problem. They upgraded their hardware, and they didn't take into account the rounding errors and or overflow errors, and they had to blow up this rocket up on launch because it was going to fall on someone's head. Finally, perhaps the most disastrous testing-related problem of all, there was a student that got a bad grade this semester because they did not write good test cases. Don't let this happen to you, please. Okay, so there's a couple general terms that you should know in terms of thinking about testing. One is called validation, one's called verification. Validation is the question of whether or not the software is solving an actual problem, or the important problem that the customer has. And so the general phrase for that is, validation is, are we building the right product? And the only way you can know that is by talking to your customers about what you're intending to do or what you have done, and seeing whether or not that's what they need. Verification, on the other hand, is checking to make sure that the actual implemented product satisfies the specification that you've developed for that product. And the phrase for that is, are we building the product right? Okay, so in that case, you don't really need to interact with the customer anymore. You're basically interacting with the specification and looking at that, and then making sure that the system actually fits that. So both validation and verification are very important. You can't always be talking with the customer, and for certain kinds of details, the customer may not be the best source of information about whether things are correct or not. So you want both validation and verification. And you can do this in both static and dynamic ways. And so by static, I mean that you aren't looking at the executing source code, but you're looking at some work product, the design, the source code, the requirements, and whatever, and you're doing an inspection or some kind of analysis on that, that work product. Dynamic validation and verification refers to looking at the system as it actually runs to see if it satisfies things, and so, for example, running unit tests, running some kind of test on the system. That's an example of dynamic V&V. Also, tests such as ensuring that it continues to perform under load is an example of a dynamic V&V process. So we have all of these different things, and we should be applying all of them during development to greater or lesser extents to make sure that we're building a product that satisfies the 3' directives. So, some questions to consider, to ponder. Is it testing if you simply run the program to see what it does? And should validation testing be done with static or dynamic testing? Should verification, on the other hand, be done with static or dynamic testing? So consider these questions and let me know what you think. Okay, testing turns out to be quite hard. It almost, in some sense, turns out to be impossible if by what you mean is we want to do tests which guarantee that the system works correctly under all possible inputs to the system. And the reason why that's impossible is because for most non-trivial systems, there's an almost infinitely large set of input possibilities, a very, very large set of system states, very large set of system states, and so testing it might take several lifetimes of the entire universe, or some very large amount of time, which you don't generally happen to have in a product development situation. So what testing boils down to is a situation in which you're going to exercise the system or look at the system under a vanishingly small percentage of all possible states that the system could be in. And from that, you are trying to extrapolate and gain confidence that the system is going to work correctly under this much larger set of states. Okay? And that's the trick. That's the trick. How can I exercise the system in a very small way, yet feel confident at the end of the day that it's going to work on a much larger scale than what I've actually tested? Okay? And so the way that we're going to try to deal with this problem, and there's science to it, but there's also a lot of art to it, there's a lot of craft to it, there's a lot of experience that goes into it. And so I can't say that at the end of this module or the end of this semester you're going to be an expert tester. That's something like, that takes years and years to master. But the sooner you embark upon the road of testing, the faster you'll get to a place where you can efficiently write tests which tend to catch important errors early in the process, and that speeds up the whole velocity of development. If you go into an organization which builds life-critical software, so space or defense or medical application areas, there are some very, very rigorous quality assurance techniques, which we won't cover in this class, which can create very high reliability software. Okay, so they're much more expensive, almost an order of magnitude more expensive than the kinds of testing that is conventional in development. So just to let you know that the kind of heuristic-y testing that we do here are not the kinds of testing that would prevent a Therac 25 problem from occurring, for example. Okay, you have to go to a much higher level of rigor. But for the kinds of development that you're likely to encounter initially in your career, this will go a long way to getting you started, at least. So we've got a few different types of classical testing methodologies. The two classical ones are called functional testing, otherwise known as black box testing, and structural testing, which is also known as white box testing. In black box testing, you're going to consider the system to be a black box, okay? Thus the name. And the idea with the black box system is that you have some inputs coming into the black box and you have some outputs coming out on the other side of the black box. And you're going to write tests that feed in some inputs, and you're going to get some outputs, and you're going to check to make sure that the correct outputs occur depending upon the inputs that you supplied it, and you're not going to worry about what's inside. The black box does whatever it does. You don't really care. And this is a very powerful form of testing, and works very well when you have a good specification that helps you understand the relationship between inputs and outputs in a very clear way. Conversely, there's a technique called white box testing. And with white box testing, or clear box testing, the idea is that you're going to actually be able to look inside and see what's going on as the code executes the test. And you're going to be able to assess the quality of the test by seeing how much of the system's internals are actually exercised as a result of running your test cases. So those are the two classical ones that we're going to talk about in the rest of this module. There's an entirely different approach actually to this, which is called test-driven development, which is a popular technique in the last, I'd say, 5 years, which involves using test development to actually drive the design of the system. So before you write any code at all, or before you write any kind of implementation code at all, you first write a test. And you run the test, and the test will fail because you haven't written the code that actually enables the test to pass. And then, once the test case fails, then you write the code to make the test pass. And you only write as much code as necessary, hopefully, to make the test pass. And then you write another test case. And then the test will fail. Maybe even the first test will fail. And then you go back and you fix things in your code so that both of those test cases pass, and you go on and on and on like that. And so you're actually using the process of testing as essentially a way to design your software, because obviously you're developing your API to your system as a result of your test cases, because your test cases are going to call classes and methods and so forth. So that's an entirely kind of different approach to the idea of how it is that you come up with your test cases, and what are you doing to make sure that your test cases are good or not. And we may experience test-driven design later in the semester. I haven't quite decided whether we'll put that in, but it's a very interesting alternative technique. And I also want to stress that you don't have to choose just one of these. So they're not mutually exclusive. You can kind of mix them up depending upon where you are in development and what you feel would be most effective. So now let's look at black box testing, okay, aka specification-based testing. And as I said before, what you're going to do is you're going to have some specification that tells you, given a set of inputs, what the output should be. And then what you're going to do is design test cases that hopefully guarantee that across all your set of inputs, the correct output will be created. And I think you can recall in the FizzBuzz program that we did a kind of specification-based testing, because we asked ourselves, there's certain inputs which should produce fizz, certain other ones which should produce buzz, and certain other ones that should produce fizz-buzz, okay? And that's kind of how we tested it, right? We picked some input values that should produce those three output values and then checked to make sure that they were actually happening. So that was a really good example, simple example of specification-based testing. And as you can see, it doesn't require us to know how the code is actually executing. All we need to do is be able to specify the inputs and then find out what the output actually was. We don't have to care about how it actually did it. The nice thing about specification-based testing is that since you're not looking at the code, the method is kind of impervious to whether or not the code's actually been implemented or not. So if you provide an input that the system goes into an infinite loop or crashes or doesn't produce any output at all because that the code to handle that kind of input was never implemented, doesn't matter. Your test will discover that. So it can catch errors of omission. The problem with specification-based testing is that you have to have a good specification in order to have good tests. So this technique is really critically dependent upon a very precise, complete specification of your system. And in certain cases, that's easily available. In certain other cases, it's not. But that's a requirement. So one way you deal when you have a specification of your system, and as we said before, you can't test all possible input values for any non-trivial system. One way that you can deal with that basic problem is by looking at your set of input values and dividing them into equivalence classes. And so your equivalence classes, the idea is that within any given set of input values, so you maybe have 100 million input values, and you divide them into 10 classes, each containing 10 million input values. And your claim that you have to kind of convince yourself outside of the testing framework, your argument is that if I test one data point from within this equivalence class, I'm effectively checking to make sure that all of those data points are going to work correctly. And then, if I've divided my system into 10 different equivalence classes, I just have to do 10 tests. And if my equivalence, if my definition of equivalence is actually correct with respect to system behavior, then those 10 test cases if they all pass, verifies that all 100 million possible input values will also work correctly. Okay, so how do we figure out what equivalence classes we should look for? And there are some heuristics. I've got allergies today. There are some heuristics that can help you design your equivalence classes. There's looking for maximum value. The maximum value that can be provided to the system would form one equivalence class. The minimum value, and that's an equivalence class of 1. The minimum value would form another equivalence class, an empty value, typical value, illegal value. And if you design for all of those, then you've maybe not got all the equivalence classes, but you've identified, in this case, 5 equivalence classes that are important for partitioning the overall data set. For sequences, for values which are sequences like lists, strings, whatever, you can look at a single element, a sequence that has no elements, a sequence that has the kind of the maximum length sequence, or a sequence with maximum and minimum element values, illegal elements, and so forth. So those are possible equivalence classes to help you with that one. When you have conditions, then make sure you test both kinds. And then if you have some kind of loop in your specification, make sure that you have an equivalence class where the loop would not be executed at all, where it'd be executed exactly once, and where it'd be executed at least more than once. So those are some things to look for with kind of numerical or primitive data type values. With web applications, you can think on kind of a higher level and say, well, one equivalence class, or the page retrieval is one equivalence class. So I want to find all the different pages in my system and make sure that my test cases guarantee that all of the pages will actually be retrieved and that there will be no errors, from rendering those pages, or that the link is actually, on each page there's a set of links and all those links actually retrieve legal pages. For forms on a web page, you test to make sure the form can be filled out in various ways in there. It doesn't lead to errors. Okay, so that's the kind of thought process that you go through, where you start with the possible input values, you look at your specification, and you design sets of test cases. Tool support for testing in this class is JUnit. Most of you have kind of fiddled around with it. Now you're going to actually read about it and learn to write test cases. Here's a simple example, and after writing a test case, there's a tool called JUnit Report, which our build system runs, and what it does is produces a nicely formatted HTML report that enables you to look through the data output by the running of JUnit in a nice fashion and see what errors occurred and whether any errors occurred. Okay, let's move on to white box testing. White box testing is the converse of black box testing. Now we're going to actually evaluate the quality of our test cases by seeing whether or not code was actually executed. And the underlying premise of this is that if there's a bug on line 52 of your system, if the bug is on line 52 and none of your test cases even execute line 52, then you're probably not going to find that bug, right? Stands to reason. So the reasoning is that in order to at least have a possibility of finding the bugs in your system, your set of test cases should be executing all the lines of code in your system, right? Now, just because a line of code gets executed doesn't necessarily mean that the bug which is present on that line of code will actually be revealed, okay, due to the complexities of how these bugs can manifest itself. However, we do know for sure that if you don't execute that code at all, then you're not going to find the bug that's there. Okay? So it's more like, the fact that the line of code is executed raises the odds from 0 that the bug could be revealed, but does not guarantee that the bug will be revealed. So we've got various kinds of way we can think about coverage. Okay, beyond statement, so that's statement level coverage. Control flow coverage looks at the in a little more detail. So it says, well, if we've got a branch, then we've got to make sure that the conditional statement, in addition to being just executed, we want to make sure it returns a true and false value. In loop coverage, we want to make sure that the loop is both not executed at all and executed more than one time. So these are kind of more fine-grained kinds of coverages that we can layer on top of our basic coverage, which is statement level coverage. Path coverage computes how many different ways, if you have a conditional followed by a loop, okay, well, you could go through the conditional, 2 different ways, and then you go through the loop either 0 ways or more than 1 way. So there's actually 4 different paths through that, section of the code, and you want to make sure that all those different permutations are taken. Okay, so beyond statement level, in this class we'll just be focusing on statement level coverage with our tool, but there are these more advanced kinds of coverages that you can check for. The tool that we're going to be using for statement level coverage is called Jacoco. It's a nice tool. Our build system enables you to run it, and what it will show you is for your system how many classes, methods, and actual lines of code were covered by your test cases. So here's an example of the output for the Decruiser system, and you can see you can start with the top level system, then you can drill down to the individual classes, and then you can look at the individual methods, and then here you can actually see the code, and you can see what lines of code have been exercised by your test cases, the green lines, and what lines of code haven't via the red lines. Okay, so it's a pretty nice system. Now here's the big fallacy and the kind of the downfall of white box testing, which is that it becomes very tempting to write some test cases, quickly run Jacoco and see which lines of code were not covered, and then just write another test case that makes sure that line of code is exercised in some way, get it to 100%, and then with a sigh of relief go, okay, my system is well tested. That's not a good idea. Okay, the reason, as I said before, is because the mere fact that a line of code was executed doesn't necessarily mean that you've revealed the bug. And in fact, if you just willy-nilly try to make sure that lines of code are covered, it's quite possible that you're not going to reveal the bugs on the line of code. Okay? And so you can end up with 100% coverage, but with a system that's poor quality and likely to break. Okay? The appropriate way to use coverage is to first design test cases, for example, based upon the specification, and then use coverage to assess whether or not your specification and the set of test cases that you wrote based upon the specification has actually done a good job of looking at the system behavior. And if you find that you write a set of test cases based upon the specification and only 50% of the code in your system is actually exercised, okay, there's something wrong. Your specification is out of date, or you haven't written a set of test cases. There's something that you're not understanding. Okay, so if, on the other hand, you start off, you have a specification, you write a set of test cases based upon the specification, and your coverage is high, 100% as a result, that gives you additional confidence, in a sense, that your approach to writing the test cases was good. Test-driven, it doesn't have to be, this black box thing. You could be using test-driven design. Okay, and at the end of that process, you could run Jacoco and say, hey, were my test cases actually exercising all the code? But my critical point is it's not the other way around. Just because you have high coverage doesn't necessarily mean that you've got good test cases. It doesn't automatically imply. So the limitations of this white box testing is that it's good for the assessment process, enables you to it helps with the process of catching bugs in the code that exists, but doesn't help at all with code that's not been written. So if you fail to implement a requirement for your software, you can have 100% coverage, but it can't exercise code that hasn't been written, or 100% coverage doesn't reveal the fact that there's actually another 20% of your code that you need to write that you haven't. Okay, so in this class, as I said before, and I'll say it again, we're going to use a combination of quality assurance techniques. We've got our automated quality assurance that we talked about previously with check-style PMD find bugs. We're also going to use manual quality assurance, code review, which we've talked about previously, and now JUnit, which is our testing piece of the puzzle. Okay, and we'll use this Jacoco tool as a way of looking at the coverage. Thanks a lot, and I'll see you later.